Okay. So welcome to lecture number 7, and in this lecture we'll be talking about transfer function. So already we have started this one in last lecture, and we have I'll take within 2 to 3 slide recap of our earlier lecture what we have studied, and then we'll start okay what we are going to study in this lecture. So you know that uh, this is the plant and this is the input to that plant, so which is given by u of t, and the output of this plant is y of t. So this is the controlled variable, and this is the reference one, right? So according to the reference, you get the okay, your plant will be controlled and you get the controlled output. So y of t is the output variable, u of t is the reference variable. So the definition of transfer function is that it is the ratio of Laplace transform of output variable, so Laplace transform y of t, to the Laplace transform of input variable u of t, by assuming all initial conditions as 0. So this is the definition of transfer function. That is, transfer function is the ratio of Laplace transform output to the Laplace transform input by assuming all initial conditions as 0. So here y of t is the output and u of t is the input. So Laplace transform u of t is this L of u of t is equal to u of s, and Laplace transform y of t, that is the output, is y of s. So where L is nothing but the Laplace operator, right? So that we have studied in our earlier lecture. So g of s is the transfer function, which is the ratio of Laplace transform output variable to the Laplace transform input variable. So y of s divided by u of s. So transfer function is basically, if you multiply the input Laplace transform input with the transfer function, you get the output. So u of s into g of s is equal to y of s, right? So that we have studied. Also, we have studied, like, for example, if you have the second order system, right, where y of t is the output and x of t is the input, and if the mathematical model of your second order system is given by like the equation like this, so where your y of t is the output and input of the system, just it should be y of t as an input here, and input x of t should be input and y of t should be the output, right? So d2 x of t, if this system is given by mathematical model like as a d2a into d2 x of t by dt square equal to c into dy t by dt minus b into dx t by dt. And if you take the so this can be written as this double dash is nothing but the double derivative and so on. So if you take the transfer function, okay, if you take the Laplace transform of this equation, you know that Laplace transform d2 by dt square is nothing but s square. So a is the constant, so a into x square. What is the Laplace transform of x of t? That is x of s. Then zero initial condition is s into x of 0 minus x dash of 0. So this is the Laplace transform of this side. Similarly, you can take the Laplace transform of this side. So if this term Laplace transform c is constant, and because of d by dt, so this Laplace transform term will be s, and Laplace transform of y of t will be equal to y of s minus y of 0. Similarly, the Laplace transform of this term will be equal to b is constant, so minus b will be there, and because of d by dt, this will be s, and x of t will be x of s minus x of 0. Then from that one, you can find out the transfer function by finding the equation of y of s by x of s, right? Now, consider, okay, by consider zero initial condition, so this will be 0 and all those things, so you get this term like okay, finally the ratio of x of s by y of s will be like this. Or if you consider y of s as output, then y of s by x of s, this will be exactly opposite, right? So you can find the transfer function by assuming the zero initial condition and so on. Now, okay, so that is what we have studied in last lecture. Now consider the general equation, like for example, the transfer function, this is the mathematical model of general mathematical model. So which is given by a0 into y raised to n plus a1 a1 into y raised to n minus 1 plus dot 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 a n minus 1 into y raised to basically this one 1, and then an into y raised to 0 here basically, right? So which is equal to b0 into x raised to m, b1 into x raised to m minus 1 up to bm minus 1 x raised to 1 and bm into x raised to 0, where the power n is greater than or equal to m, and where x is basically the input and y is the output of the system. And you know that the transfer function is given by g of s, which is equal to L of output, Laplace transform of output variable to the Laplace transform of input variable by assuming 0 initial condition. So initial conditions are 0. Now, if you take the Laplace transform, okay, so already this one, you can find out the value of y of s by x of s, which is equal to see that b0 into s raised to m plus b1 into s raised to m minus 1 plus up to this one, and then divided by a0 into s raised to n, and so on. So this is the transfer function of this system, and you know that this is the denominator of this transfer function, and this is the numerator of this transfer function. So general equation of transfer function means basically you are taking the Laplace transform of output variable to the Laplace transform of input variable by assuming 0 initial condition. Now we'll see what is by proper transfer function and what is by improper transfer function. So see that this is the denominator term or denominator polynomial of this transfer function, where x of s is nothing but the input variable, y of s is the output variable, and okay, in general basically the value of c for the proper transfer function, the value of n should be greater than or equal to m. Okay, so strictly proper transfer function, n should be greater than m, right? So when order of the this order, what is by order and the type, that we'll see later on, but the highest power of n in the denominator is nothing but the order of system. So when the order of the denominator polynomial is greater, see, this is the denominator polynomial and this is the numerator polynomial. So what is the order of, okay, order of the denominator polynomial? That is n. What is the order of numerator polynomial? That is m. So when the order of denominator polynomial is greater than the numerator polynomial, means n is greater than or equal to m, then that transfer function is said to be proper transfer function. Okay, and for strictly this one proper transfer function, this value of n should be greater than m. It should not be equal. Okay, it is greater than 1. So then that is called as the strictly proper transfer function. But if n is greater than or equal to m, then this transfer function is considered as a proper transfer function. And otherwise, if n is less than m, then this transfer function is considered as a improper transfer function. Now, what is basically physical significance of proper transfer function and improper transfer function and strictly proper transfer function? So basically, in a proper transfer function, that system is realizable. Okay, strictly proper transfer function and proper transfer function is that system is realizable, whereas if the transfer function is improper, then that system is not realizable in practical. Right, realizable means what happens basically, even if you increase the frequency, okay, you don't get the output infinite or undefined output or infinite output in case of proper transfer function. Even if you increase frequency right from 0 to infinity, the output is basically well defined and it is a bounded output and so on. But in case of improper transfer function, if you increase the frequency, there is no guarantee that your output will be bounded. It may be unbounded. Unbounded means it will go beyond the limit, and because of that, system may get damaged or it may get burned and so on. So for the system to be stable, your transfer function should be proper. Okay, for the system to be stable, your transfer function should be proper. So the value of s, this one n, should be greater than or equal to m, then that system is considered as a proper, okay, or that system is having a proper transfer function, and so on. I hope that this is clear to you. And what is it, what is it by proper transfer function, what is by strictly proper transfer function, and improper. Once again, I'll repeat it. See that if this is the general equation of the transfer function, where, okay, this is the denominator polynomial and this is the numerator polynomial, y of s is the output, x of s is the input variable. Okay, you know that Laplace transform output variable to the Laplace transform input variable is nothing but the ratio of Laplace transform output variable to the Laplace transform input variable is nothing but transfer function, and this is given by this one. Right now, this n, n determines the order of the system. Okay, as I told you that we'll study order and the type of the system later on. So this value of n should be greater than n, right? Then that system is considered as a strictly proper transfer function. But if value of n is greater than or equal to m, then it is called as a proper transfer function. Okay, in strictly proper transfer function, this equal to is not there, so n is greater than m equal to m. It means your system is absolutely stable in that case, and it is realizable. And okay, in case of proper transfer function, what happens basically? So sometimes it may happen that n is equal to m. So basically, this n tells you that how many poles are poles are there, and m it tells that how many zeros are there. Okay, so this improper transfer function is that if n is less than equal to, or less than m, then that system is considered as an improper transfer function. So proper or strictly proper transfer function are practically realizable. We can implement those systems, and those systems will be stable even if we change the frequency from 0 to infinity. For that range, your system will remain stable in case of proper and strictly proper transfer function. Whereas in case of improper transfer function, value of n is less than m, and that system is unrealizable, and there is no guarantee that your system will remain stable or it will not be realizable, and so on. So generally, systems should have proper transfer function, or ideally it should have strictly proper transfer function. I hope that this is clear to you. What is the transfer function? Now, what is the use of transfer function particularly? So the transfer function can be used to check the stability of the system. Okay, we'll see in our fourth chapter how we are going to investigate the stability of the system from the transfer function. So one of the use of transfer function is that to find out the stability, system stability, we need a transfer function of that system. Then second use of the transfer function is that time domain and frequency domain characteristics of the system can be determined from the transfer function. Means we can determine the time domain characteristics as well as we can determine the frequency domain characteristics of the system from the transfer function. Okay, and third use of this transfer function is that a response of the system for a given input we can determine. Like, see that if we know okay, transfer function, so this is known, and then if you have the unknown value of x of s, that is input is unknown, still we can determine the output. So y of s will be, what happens basically, if you take this x of s to the right side, it will get multiplied with this transfer function. So multiplication of transfer function with the input, that will give you the output. So even if your input is okay, unknown, or basically known, then you can find out basically this one output. So a response of the system for a given input can be determined with the help of transfer function. So these are the three uses of transfer function. One is we can find out the stability of the system. Second one is that we can find out the characteristics of the system in time domain as well as frequency domain. And the third use of this transfer function is that we can determine the response of the system for a given input. So whether that input is a step input or parabolic input or ramp input or sinusoidal input or this one impulse input, any kind of input if you have, we can determine the output of that system if you know the transfer function, right? So these are the three uses of the transfer function. Now, next point is that what is the advantage of transfer function? What kind of advantages are there of the transfer function? So first advantage of the transfer function is that it is a mathematical model. See that whatever we got, this is the mathematical model of a physical system. Okay, so it is a mathematical model that gives the gain of the given system. So after all, this transfer function is nothing but the gain. So this is nothing but the gain. G of s is nothing but y of s, Laplace transform y of s divided by Laplace of u of s. So this is the gain of the system. Basically, transfer function is nothing but the gain of the system. So it is a mathematical model that gives the gain of the given block. So that is the first advantage of the transfer function. Second one is that it uses Laplace transform. The terms are simple algebraic equations. See that I told you that even if you have a higher order integral differential equation, but after taking the Laplace transform, this equation will become simple algebraic equation. So simple algebraic expressions are there, and these integral differential equations or terms are absent in that. So in a transfer function, you will get only simple algebraic equation, okay, instead of integral differential equation in time domain, right? Then third advantage is that once transfer function is known, then output for any input can be found, or so you can determine the output for a given input if you know the transfer function. So that is the third advantage of the transfer function. The fourth advantage is that if you factorize this one, see that if you find out the roots of this denominator, these roots of the denominator are nothing but poles. We'll see what is the poles and so on. And the root of this numerator of transfer function are called as zeros. So from the transfer function, we can determine how many zeros are there and how many poles are there. So once the transfer, okay, from transfer function, poles and zeros can be found. And once you know the poles and zeros, you can tell whether that system is stable or unstable, right? So from the characteristic equation, the system stability can be found or inferred. So what is my characteristic equation also will study in next slides and so on. Generally, your denominator, if you equate that one equal to 0, so that equation is called as the characteristic equation, because from that we can find out the stability of a control system, or we can determine the characteristic of that control system. That's why it is called as the characteristic equation. So there are 5 advantages. Number one is that it gives, transfer function gives the mathematical model, and that is nothing but the gain of a given block. Second thing is that for finding the transfer function, we use the Laplace transform. So this Laplace transform will convert higher order integral differential equation into simple algebraic equation. So solving those equations are easy. Okay, so that is second advantage. Third advantage of transfer function is that once you know the transfer function, you can determine the output for given for any given input. Okay, so that is the third advantages. Also, fourth one is that, see, the roots of denominator are called as the poles. So if you find out the roots of the denominator of transfer function, you'll get the information about the poles. And if you find out the roots of the numerator of the transfer function, that is called as the zeros. So poles and zeros we will know from the transfer function. And the last one is that if you equate the denominator of that transfer function equal to 0, so that is called as the characteristic equation. And from characteristic equation, by observing the characteristic equation, we can tell whether that system is stable or unstable. We can find out the characteristic of that equation. So we we can from the transfer function we will know the stability of a control system. So these are the 5 advantages of transfer function. Okay, now what are the disadvantages of transfer function? So first one is that as per the definition of transfer function, this is valid for LTI system, that is linear time invariant system. Okay, it is not applicable for linear time varying system, or nonlinear time invariant system, or nonlinear time varying system, and so on. So this is applicable, this definition is applicable only for LTI system, that is linear time invariant system. So we have studied what is by linear system, what is by time invariant system and time varying system, and then what is by LTI system, right? So first disadvantage is that, or limitation we can say, that is that transfer function is valid only for LTI system, right? Second disadvantage of transfer function is that it does not take into account the initial condition. See that as per the definition itself, we are saying that by ignoring the initial condition. So transfer function is nothing but that it is the Laplace transform of output variable to the it is the ratio of Laplace transform of output variable to the Laplace transform of input variable by assuming zero initial condition. So we are assuming zero initial condition. That is in ideal case, but in practical case, sometimes it may happen that there are some initial conditions, so which we are ignoring for finding the transfer function. So it doesn't take into account the initial conditions, and initial condition loses its significance in the transfer function, right? Third disadvantage is that it doesn't give any idea about how the present output is progressing. No idea about physical structure of the system is immediately known. So look at this one. If you know the transfer function of the system is like this, can you tell, okay, what kind of physical components are there and how they are connected and so on? So by looking at the transfer function, you cannot tell that one. So this is okay. This is one of the disadvantage of the transfer function, that you don't get any idea about the physical structure of the system immediately and so on, and it does not give any idea about how the present output is progressing, right? So these are the three disadvantages of the transfer function. So we have studied what is the use of transfer function, is basically what is transfer function, what is proper transfer function, what is strictly proper transfer function, what is improper transfer function, its physical significance. Then after that we have studied what is meant by what are the uses of transfer function, then what are the 5 advantages of transfer function, and what are the 3 limitations of transfer function. So that is what we have studied up to this point. Now, what are the properties of the transfer function? So transfer function is independent of the input to the system. See, once you determine the transfer function, okay, so this is independent of the input. It is not dependent on the input, but your output depends upon the transfer function and the input, but transfer function does not depend upon the input. So to find out the transfer function, generally impulse response is taken, right? Impulse, by taking the impulse response, you get the transfer function of the system. So transfer function is independent of the input, but your output depends upon what? This one, your transfer function as well as input. So transfer function is independent of the input of the system, and the poles and zeros can be found from the transfer function. Then third property is that the stability can be determined from the characteristic equation. Fourth one is that the transfer function is defined only for LTI system. It is not defined for the nonlinear system. And then if n is greater than m, the transfer function is strictly proper. If n is equal to m, transfer function is proper. And if n is less than m, transfer function is improper. So this is acceptable for realizing the system practically, but this is not acceptable for realizing the system. So these systems may be stable, okay, this system may be unstable, and so on, right? So by looking at the transfer function, you can tell whether that system is stable or unstable, or whether that system can be realizable in practical condition or not, so that you can tell by looking at the transfer function. Now we will see the concept of poles, zeros, and stability, right? So up till now, we have studied what is transfer function, then strictly transfer function, proper transfer function, improper transfer function, physical significance of that one, uses, advantages, disadvantages, and properties of the transfer function. Now, the next part of this lecture is okay, understanding the concept of poles, zeros, and stability. Now, what is by stability of a control system? We have okay, 4th chapter of control system stability. So there are several meanings of stability in a control. In general, there are 2 kinds of stability: absolute stability and relative stability. So basically, okay, we'll study what is by absolutely stable, what is by relatively stable, what is by marginally stable. All those things we are going to study in our fourth chapter. Okay. See that our definition, I can tell you what is by stability. So for the bounded input, you get the bounded output. Okay, and if the input is absent, your output will be 0 at that time. So for the stable system, for bounded input, you get the bounded output. And if input is absent, your output will be 0. So that system is called as the stable system, right? Okay. Now, what is by poles and zeros? So this, as I told you, that this is the denominator polynomial. And if you find out the roots of this denominator polynomial, those roots are called as poles. So the roots of denominator polynomial of a transfer function are called as poles. Whereas if you find out, this is the numerator polynomial of the transfer function, and if you find out the roots of this numerator polynomial, these roots are called as zeros. So the roots of the numerator polynomial of a transfer function are called as zeros. So these roots of numerator are called as the zeros, and the roots of denominator are called as the poles. Right? Now we'll see what is the physical significance of poles and what is the physical significance of zeros. Generally, the stability of a control system is determined by poles, right? Right. So poles of the system are represented by cross, okay, and the zeros of the system are represented by 0, right? See that what first thing is that we have studied what is by pole. Pole is nothing but the roots of the denominator, and zeros is nothing but the roots of the numerator, right? Now these poles are represented by in standard way by cross mark, and the zeros of the system are represented by 0, right? System order is always equal to the number of poles of the transfer function. Okay, so system order, see that since poles are associated with your denominator, and this n will tell you the what is the order of the system. So if n is equal to 5, then that system is considered as the fifth order system. If n is equal to 10, then that system is order is considered as a 10th order system, and so on. So this value of n will tell you what is the order of that system. If I say that fifth order control system means the value of this n is equal to 5. So system order is always equal to the number of poles of the transfer function, and following transfer function represents the nth order plant. So this is the nth order plant having transfer function like this, right? Now see that poles is also defined as it is the frequency. See that this poles is nothing but the roots of this denominator. So definition of this pole is that, see, you get, suppose for example, you get 5 poles or 5 roots. Okay, so it is also defined as it is the frequency at which system becomes infinite. Like for example, if I have s is equal s plus a, s plus b, or s plus a1 plus s plus a2 plus s plus a3. So like that way, I have 3 poles. So if I put s is equal to s plus a equal to 0, so value of s will be equal to minus a 1. So minus a1. So at that time, okay, system transfer function will become infinity. So at that frequency, your system transfer function will become infinity. So poles is defined as it is the frequency at which system becomes infinite, and hence the name pole, where field is infinite. So pole is infinite. Whereas, so for example, we have zeros, like as 3 zeros are there. Like for example, s plus b1 is 1 0, s plus b2 is another 0, s plus b3 is third 0. So if I put s plus b1 equal to 0, so that will be value of s will be equal to minus b1. S plus b2 equal to 0, so value of s will be equal to minus b2. Now if I put the value of s in this term as s equal to minus b1, then the whole system transfer function will become 0. So that's why it is called, that root is called as the zero of the system. Whereas, as I told you that if I put the value of s equal to the root of that one, then that system transfer function become infinity, and that's why it is called as a pole, right? So poles is also defined as it is the frequency at which system transfer function becomes or system becomes infinite, and hence the name pole where field is infinite, whereas 0 is nothing but the root of the numerator, and for that value of root, okay, value of s, your system transfer function will become 0, so that's what is called as the 0. So poles, like for example, this is the example of your transfer function. So transfer function is given by 10 is the gain of the system, and numerator is s plus 2, okay, and denominator is s plus 1 and s plus 3. So how many poles are there? See, numerator, how many roots are there in the system transfer? See, this is the system transfer function. How many roots are there in the denominator? There are two roots. One root is located at -1 and another root is located at -3. Now, if I put the value of s is equal to -1, what will happen here? -1 plus 1, so this term will become 0, and if anything divided by 0, that will become infinity. So if we put the value of s equal to -1, your transfer function will become infinity. That's why this is called as a pole. Similarly, if I equate that s plus 3 equal to 0, so value of s will be equal to -3. Now, if I put the value of s equal to -3 here, so -3 plus 3, this will become 0. So anything divided by 0, that will become infinity. So this term, these roots are called as the poles. But now see that there is one 0 here, right? S plus 2 equal to 0. If I equate that s plus 2 equal to 0, so what will be the value of s? That will be equal to s equal to -2. Now, if I put the value of s in entire equation, s is equal to -2, so my numerator will become 0, and whatever may be the denominator, if numerator is 0, my transfer function will become 0. So this root, this value is called as 0, whereas these roots are called as the poles. So the poles of a Laplace function are the values of s that makes the Laplace function evaluate to infinity. They are therefore roots of the denominator polynomial. Okay, so complex pole always appear in complex conjugate pair. Okay, we'll see these are the simple real pole s at s, because it will appear on the real axis, s is equal to -1 or s is equal to -3. Also, this is the real 0 which will appear on the real axis at s is equal to -2. So complex pole always appear in the complex conjugate pair, and the transient response of the system is determined by the location of the pole, right? Now, see that the poles is defined as it is the frequency at which system becomes infinite. So these roots of the denominator are called as the poles. So at which if you equate put those value of roots in the denominator or in entire equation, this one transfer function, your transfer function at that frequency will become infinite. So poles is also defined as it is the frequency at which system becomes infinite, like magnetic pole and so on. So I hope that you have understood the concept of poles and zeros. Now in our tomorrow's lecture, we'll see how to plot the poles and how to plot the zeros, and then what is the response at various locations of the poles, and whether the system remains stable or unstable. So that part we are going to study in our tomorrow's lecture. So today we'll stop here. If you have any question, you are free to ask the question, and thank you very much. Just 1 minute. Okay, if you have any question, you can ask. Okay, my mic is